All right, greetings everyone. Welcome to Love, Laugh, Learn. I'm Doc Eason, and in today's video, I'm going to talk about the fourth dimension. So in an earlier video, I discussed the space-time concepts, and I wanted to make some clarifications to make sure you understand exactly how you go about trying to understand what that fourth dimension is, but really more specifically what it is not. So I'm going to talk about why time itself is not the fourth dimension, and actually it can never be the fourth dimension. All right, so we'll discuss that, and I'll give some reasons for that. So if that sounds interesting to you, well, stick around. All right, so to try to explain why the time itself can never be the fourth dimension, let's kind of recall a little bit the kind of situation we're talking about. Remember, there was a previous video that was made where I discussed the space and time concepts. And I mentioned in that video that a scientist by the name of Lorentz, towards the end of the 1800s, had worked out a transformation known as the Lorentz transformation that relates position and time in one coordinate system or reference frame to that of another. And so I also mentioned a kind of an example where I mentioned a person standing on the side of a train, and the train, for example, was moving. So in this particular example, the moving frame would be the train, and the stationary frame, or the frame from which relative to which this motion is taking place, it would be the ground. So this would be where the person is standing on the ground, and they would, for example, want to measure the speed of light from this reference frame. And then the person, as far as in the X, Y frame and Z frame, this is the frame of the train. So the moving train, which has a velocity U. All right. So just to kind of put some physical picture on that. And these are the Lorentz transformations. And don't worry, you don't have to understand exactly what these are saying. I want you to actually understand the similarities and the differences based on what existed previous to Lorentz transformation. So over here on the left, you'll see what's called Galilean transformation. And this is, some of you know, this may be more of an intuitive result that you're familiar with, where you relate the position in one frame to that of another where the frame has some motion. All right, one of the reference frames has a motion U. So this is what we're used to in classical, basically classical physics. But what Lorentz found was that when you have the situation where light, again, has the same speed in all these different reference frames, it can't go any faster than what we denote by the letter C, which is 3 times 10 to the 8 meters per second. Then what he found was relationships that look like this. And the thing I want you to notice is the difference between the way time is described in the Galilean transformation, where time is equal between these two frames in a Galilean transformation. So this is a major difference compared to what Lorentz found. So notice that how position depends on position and time between the two frames, even in the Galilean transformation. And this is also true in the Lorentz, but in a more general way. Now, time, however, changes more significantly because now you see time is also related to both the time and the position, which is R, in the other frame. So this is the same thing as can be said of R. R depends on position, or the position depends on position in the other frame as well as the time. And now the time also depends on time and position in the other frame. And this is the major distinction between Lorentz transformation and the Galilean transformation. And it is this simple little difference that actually causes a significant change in the way the equations and descriptions of physics, actually moves in slightly different directions, particularly for systems that have motion that can be large compared to the speed of light, which is the c. All right, so that's the picture here, and this is the difference, and this kind of the significance of Lorentz transformation. So now let's get to the point, at hand, which is, why is it that time itself, I know you see this equation for time, but why is it that time itself cannot be a fourth dimension? It simply doesn't qualify. And so let's discuss that. So let's come over here and look at our little diagram, our nice diagram here. And And if you look over here on the left, this is just a diagram of a 2D space. And remember, we have a 1D axis and then a 2D, for the 2D axis, then there's another one which is just 90 degrees from the 1D. And these axes allow us to describe not only X, but changes in X, or not only Y, but changes in Y. And this is the reason why we need two directions. We got to be able to go both for positive numbers and negative numbers. All right. So when we look at this, one of the things that you'll notice, and I'm sure you have some experience that agrees with this, but if you are able to walk in a straight line, let's say along Y, and you can do this without changing your location in X. I'm sure you've done this before. So if you can walk in a straight line. You're free to walk, of course, let's say at any line you want. Let's say at an angle where there'll be variation in both Y and X. However, it is certainly possible to walk along Y in such a way that it does not require or necessitate a change in another dimension, in this case, in X. And I can do the same in X. I can walk along a horizontal line as free as I like, and it doesn't require or necessitate a change in Y. All right. So these are properties of any dimension. So if I'm going to have a dimension, changes in one of them certainly doesn't dictate or necessitate a change in any of the others, because then they would be dependent on one another and they wouldn't qualify as dimensions. And so this is the distinction we want to make sure we understand when it comes to X, Y, and Z. And this is where the problem comes in when it comes to time. Because remember in our previous video, when we discussed the space and time concepts, we mentioned that it was in fact true that a change in X or Y and or Z always necessitates a change in time. I can't change a position in X without also changing time. And that was also, you can also see that in the way that the differences in the coordinates, even in Galilean transformation, you see X, you also see T. But because of this relationship and this kind of change in space always necessitating a change in time, this means that Y, X, and Z always depend in some special way on time. So they're not independent of one another. So a change in Y, again, always leads or necessitates a change in time. Unlike a change in Y does not necessitate a change in X, and so on. So we can see that more clearly with X, Y, and Z, but when we start to discuss something similar between space, the spatial coordinates, and time, we run into this problem. So that's what is written over here, where I can say that delta Y, and delta is the mathematical the symbol for changes. So this delta equals change. So a change in Y does not necessitate, that's what this is supposed to represent, just crossing out, does not necessitate or require or lead to a change in X. And so that's basically saying that these are independent of one another as a dimension should be. However, when it comes to looking at changes in space like X, Y, and time, this is not true any longer. Changes in X, changes in Y, and changes in Z will always lead to a change in time. And this is the main reason why time itself can never be actually a dimension. It simply doesn't qualify. And this is because the fundamental relationship that it has with space. This is, not our doing, but this is we can observe these things. And of course, all of the theories that agree with our physical experiences are all consistent with this, that these spatial coordinates always depend on time. Okay. So it's not possible for time itself to be a dimension. And now you could also throw in this argument that you could just, in terms of the units, because if we're talking about space, then time is, say, some unit of time. So that couldn't be a dimension. But unfortunately, that doesn't qualify as an argument, because one could just multiply time by c, the speed of light, which is meters per second or distance per unit time. And that would lead to a dimension of, a unit of length. And even c times t would not qualify for the exact same reason that I just said. Because if I change X, then so too would C times T. It would also change necessarily. And there would be there's always some dependence between these variables, considering the form of these numbers. All right. So this is the reason, the fundamental reason why time itself cannot be the fourth dimension. All right. Now, interestingly enough, this definitely means that we've got some work to do, because we know that this is not the fourth dimension. Then we need to find out exactly what the fourth dimension is. All right. There we go. And there it is. So this is why time is not the fourth dimension.